Alright, so this is a large example that puts together what we learned in chapters 19 and 20. So we have a diatomic gas of 0.5 moles that undergoes a cyclic process. The process from 1 to 2 is adiabatic, from 2 to 3 is isobaric, and then 3 to 1 is isovolumetric. And we know what the initial temperature of the system is, so at 0.1, and we want to know what the net work of the cycle is, what the net heat is, and then the change in internal energy, and then assuming it's a heat engine, we want to know what the heat efficiency of the engine is. Alright, so you can see out to the side here, the first thing I'm doing is finding the temperatures. So we know from 1 to 2 is adiabatic, so I can use my relationship for temperature, volume, and the adiabatic index in order to find temperature 2, because I know temperature 1 and volume 1, and I know volume 2. And since this is diatomic, remember the adiabatic index is molar specific heat at constant pressure divided by molar specific heat at constant volume, which would be 7/2 divided by 5/2 times R for the diatomic gas, which reduces down to 7/5. And since the process from 2 to 3 is isobaric, I just use then the ideal gas law because I know the pressure and the volume and the number of moles in order to find the temperature at 0.3. So from 1 to 2 we're adiabatic, and don't forget you should be looking at that table provided in chapter 29. So when you're adiabatic, Q is going to equal to 0, and work is going to be the negative change in internal energy. So I'm going to find the change in internal energy using number of moles times molar specific heat at constant volume times change in temperature. So I'm plugging in 0.5 times 5/2 times the ideal gas constant and change in temperature. And you have to be very careful about changes in temperature because we're going to 1 to 2, you're doing temperature 2 minus temperature 1. So temperature 2 was 276 and temperature 1 given the problem was 746 Kelvin. So we get our change in internal energy, which we then can plug in over here in order to get the work. So we're good from 1 to 2. From 2 to 3, we're isobaric. So heat is calculated by number of moles times molar specific heat at constant pressure times the change in temperature. So we're going to take our 0.5 moles times 7/2 times our ideal gas constant, and then we're going to do 3 minus 2. So 3 was the 24 Kelvin, and 2 was the 276 Kelvin. So we get the amount of heat. Work is calculated through pressure times the change in volume. So I'm reading my pressure off of the graph, and then my two volumes off of the graph. Remember, you're subtracting 3 minus 2, so 0.1 meters cubed minus 1.2 meters cubed. And then to get the change in internal energy, we're going to do number of moles times molar specific heat at constant volume times change in temperature. So our number of moles and the molar specific heat at constant volume hasn't changed, but our change in temperature has. So we now need to do 3 minus 2, so 24 minus the 276, which gives us a negative 2 times 10, or negative 2.62 times 10 to the 3 joules. And then we need to do isovolumetric, because that's 3 to 1. So in this case, work is going to equal to 0 because we have no change in volume. So Q and delta U are going to equal each other. So we're going to do number of moles times molar specific heat at constant volume times the change in temperature, remembering to do 1 minus 3. So 746 minus the 24. And since these two are equal, we're now done with those calculations. So we can take and add our three works together. So we have work, adiabatic work, isobaric work, and then isovolumetric work. And then we can add together our three Qs, so adiabatic, isobaric, isovolumetric. And notice we get about the same, so there's going to be some variations based upon rounding, especially with the rounded the temperatures. And you're also reading off the graph. I tried to make them pretty close to something you could see, but there's definitely some estimation from the graph as well. So these are pretty close to each other. And then we expect the change in internal energy, because this is a cyclic process. At the end of 3, you're back to where 1 is. When we add the change in internal energy from the adiabatic process with the isobaric process. With the isothermal, we expect it to be about 0. Now we need to calculate the efficiency of the engine. The efficiency, so we have to take our work, so we calculate our work back here in part A, but we have to be careful. QH is always energy in, so we need to look for positive Q values, which is going to be the one for isovolumetric. So we're going to take that, the work the engine does, divided by any of the positive heat values, and we get efficiency of about 0.5.